Okay, so welcome everyone. Thank you for joining us for the DeFord Lecture Series. My name is Elizabeth Catlos and I'm a faculty member in the Department of Geological Sciences at the University of Texas at Austin. We're part of the Jackson School of Geosciences, and the DeFord Lecture Series is our departmental seminar series. It's been a requirement and tradition for all graduate students since the late 1940s. The lecture series is named after Professor Ronald DeFord, who joined the university as a professor in 1948 with the purpose of enhancing the quality of the graduate program of the department. Our lecture series is supported by a series of endowments, and today's speaker is the Fred L. and Francis J. Oliver Lecturer in Texas Hydrology and Water Resources. The lectureship was created in 1985, and this speaker will be our 35th Oliver Lecturer. Fred and Francis Oliver created the lectureship because they believe the study of water resources in Texas is as important as the development and exploration of oil and gas. They established the lectureship with the goal of providing better education concerning water problems being faced by Texas and solutions to those problems. Fred received his Bachelor of Science in Geology from the University of Texas in 1951. He's a current member of the Geology Foundation Advisory Council. He resides in Dallas, Texas, where he's president of PVT Inc. In 2009, Fred's family established the Fred and Francis Oliver Endowed Scholarship in their honor to recruit graduate students into the field of hydrology. Our speaker will be introduced formally by Dr. Dan Breaker, who's an associate professor in the Jackson School of Geosciences. Dan?
Thanks, Liz. Jérôme comes to us virtually today from the Institut de Physique du Globe de Paris, and it's late in Paris, so we need to thank him especially deeply for joining us. Well, Jérôme has done quite a lot with his career, but some of the highlights here are that he has coordinated the French network of critical zone observatories, and he was also awarded a medal from the French National Center for Research, the CNRS, for the quality, originality, and the importance of his work. And he's also a fellow of the European Association of Geochemistry and of the American Geochemical Society. And he's gonna talk to us today about what he's perhaps best known for, the geochemistry of rivers. And Jérôme is really a world leader in this field. And so I think that we're all gonna enjoy his presentation very much. So thanks, Jérôme, and I'll hand it over to you.
Thank you, Dan. So thank you for the invitation. I must say that I was a little bit surprised of the time of the presentation. It's the first time in my life I'm giving a talk so late. So please excuse me if I say strange things. It's due to the very to the hour here. So initially, I gave a title to Dan, which was about what the chemistry of rivers tell us about critical zone processes. And while preparing the talk, I realized that I was probably too ambitious. So I have restricted my topic to today. And I will talk mainly on one application, actually, of river chemistry. And I will take the example of a recent paper that we have been published, which is to establish the complete mass carbon budget of a big watershed, which is a Mackenzie river basin in Northern America. So I'm still talking about the geochemistry of river tonight, but I will restrict my topic to the Mackenzie River Basin. Okay, so we use big rivers or rivers in general because rivers have this nice property of integrating things, and the integrating actually the continental crust, the upper continental crust, and they're integrating the processes and the sources, like a volcano is integrating the deep earth. And so basaltic rocks have been studied by geochemistry for multi-decades to get information about the mantle and the partial melting of the mantle, and the philosophy with which I've been working so far is to use rivers in the same way to gain information about chemical weathering of the crust and basically to understand the origin of the critical zone. So I have pronounced the name of this thin layer at the surface of the Earth that we call the critical zone. And so basically, I don't want to enter into the details about what is a critical zone and what are the limits of the definition, but basically, you should remind that the critical zone is zone which lies between the rocks, the unweathered rocks of the lithosphere, and the lower atmosphere. It's a critical zone because it's one of the critical limits, interfaces of the planet. And it's a critical zone also because this is where we live, where humans live. And this term critical was really well chosen because it's giving to this zone of interest a major philosophical and political role in the global change that humans are experiencing. This zone is critical because we need to protect it. So the critical zone is a complex thing. It's a multi-compartment object. It is comprising the so-called ecosystems, the vegetation. It's comprising the soil, the classical definition of soil. It's also fractures within in which water is circulating. It's comprising the water, of course, and it's animated by a number of processes, and a couple of these processes are represented on this slide: precipitation, chemical weathering, which is a major process which is forming the critical zone, which is transforming the rocks into a porous clayey mineral zone at the surface of the planet. And so I'm using rivers as integrators of the critical zone, both the source of elements in the rivers and the processes which are occurring in the critical zone. So rivers are nice because they are integrating over large surface areas, but of course they have the drawback that depending on the scale that you're working at, you're not going into details. And of course, if you want to go into details and to study one single process, you should go to a very small scale. But the scale I'm going to look at today is a very large scale. So I'm not going into the detailed process, but I'm using rivers as I said, integrators of these processes at the continental scale. So rivers do the average. This is a main advantage, and this is why rivers have been used in the geochemical literature. Here is a couple of slides of rivers I particularly like because I've been working on them. You have here the Congo River. Here, a very different river, which is flowing through the Himalaya, is the Changyang or Yangtze-Kiang River in China. This is the Amazon here. At the bottom here. And here is a small catchment in Laos, which is the Wepano catchment in Laos, which is characterized by very high physical erosion rates, as the picture is showing with the ice suspended sediment load. So the critical zone is formed by chemical weathering. So let me remind you what chemical weathering is in a couple of words. So basically, chemical weathering is a loss of mass. And this slide is showing one of my preferred object, which is a volcanic bomb from the Lesser Antilles. And we've been working on this rock quite a lot with my colleagues Peter Sack and Lin Ma from El Paso. You can see on that slide the center of the rock is made of an andesite, which is not weathered. Okay, it's a typical andesite. The density is 2.7, the porosity is almost 0, and the aluminum content is 18%. But when we analyze and when we look at the yellow external rind that you can see on that slide, it's totally different. It's derived from the transformation of the andesite, but it's totally different. You see a density which is very low, you see a porosity which has increased a lot, and you see the aluminum content, which is now 30%. So this simple example shows you what chemical weathering is. It's a loss of mass. Between the gray part and the yellow part of the slide, some elements, which are essentially the cations, calcium, magnesium, sodium, and potassium, has left. And they have been transported by river, by the water, which is continuously weathering the rock. And of course, the material which is remaining has lost a lot of its initial mass. And the elements which are remaining in the yellow part of the rock are the most insoluble elements, which are, for example, aluminum or titanium. And so where the cations now, the cations have been transported by water, okay? They have left the system. And when we look very simply at the composition, the chemical composition of a basaltic river here, represented on this diagram, we do see that the major elements, so most of the mass of the dissolved matter, which is in a liter of water, is made of sodium, potassium, calcium, and magnesium, which are exactly the elements which have left the weathered pellicule of the previous rock I have showed you. So basically, the weathering process can be seen as a giant neutralization reaction. The acidity is the atmospheric CO2, and it's not water, which is weathering the rocks. It's the acidity contained in water, and the acidity can come from different sources, and I'm going to show you different examples today. And so this acidity combined with water is transforming the rocks into something else. And this something else is the critical zone, and the critical zone is destroyed by physical erosion, and ultimately all the soluble and insoluble elements will get transported to the ocean by rivers. So by studying rivers, we have an idea, we get information about these weathering processes at various scale, and in particular at global scale. I would like to mention that this idea that chemical weathering is a neutralization reaction is not absolutely not new. And you can find very old articles back in the middle of the 19th century from this very famous German chemist, Gustav Bischoff, or this French mine engineer, Ebelman, which have initiated the idea, or found the idea that the weathering was a neutralization of air acidity by the lithosphere. And so this mechanism of weathering is very important for the planets, because it is transferring calcium, magnesium, and other cations from the continent to the ocean, and these cations are precipitating into the ocean. And for example, the best example is the formation of carbonate in the ocean. And this is, I have showed you here, the so-called UA reaction, which is basically the reaction of calcium silicate, typical of the crust, of the continental crust, with the atmospheric CO2, will form ultimately a calcium carbonate in the ocean plus a waste, which is dissolved silica. And this picture, which is a picture of a French atoll in the Pacific Ocean, is kind of a summarizing what is happening at the global scale. You have here in the center basaltic rocks, which are being weathered. The calcium is moved from the land to the ocean, and it's precipitated in the form of carbonate. But in the meantime, the CO2, which has been used to weather the basalt, is now sequestered in the carbonate. So this reaction has allowed the planet Earth to lower its initial atmospheric CO2, which was very high and close to what it is still now on Venus or Mars, to something which is very low and compatible with a temperature, a climate and a temperature which is good for life and the development of life. So I'd like to show you a couple of slides on the history of potamochemistry. If I can say so. Potamo in Greek means the river, and the potamochemistry is the chemistry of rivers. And it's very interesting when you start to look at when people started to publish data on river chemistry. You can go very far in the past, and some of the seminal papers have been published by a guy named Livingstone in the US in 1963, and Maybeck in Paris, and Martin published a number of important papers where they started to summarize and to put together data on river chemistry. And of course, there is a seminal book by Garrels and Mackenzie, which is 1972, which is using the river chemistry database to infer information about the denudation rates of continents. So before 1981, essentially river data were used to infer information about the denudation rates of continents or the crustal evolution, this kind of thing. And there is one significant paper which is very well known by Gibbs et al. In Science in 1970, which is trying to determine the control of a river dissolved, the river chemistry as a function of evaporation, lithology, precipitation, etc. This is a very important paper. But something happened in 1981, which is a publication of a very famous paper in the geochemical community, which is the paper by Walker et al., which is basically assuming that the Earth climate is stabilized by a feedback in which silicate weathering acts as a feedback mechanism, as a buffering mechanism. Basically, the idea of the paper is to say that if you have a lot of CO2 in the atmosphere, temperature is going to increase, and then the weathering of silicate is going to produce more calcium to the ocean, and you will precipitate more carbonate into the ocean. And then you have a mechanism which is able to stabilize the Earth climate. This was a very important paper, and this is still a very important paper, but my point today is to show you that this paper has triggered a total phenomenal increase on the number of papers on rivers, because suddenly people working on rivers realized that the data that they were measuring and accumulating could be very useful to test this thermostat hypothesis, the paper of Walker and et al. Published in 1991. So after 1881, the introduction of the paper dealing with the geochemistry of rivers mentioned the fact that silicate weathering was a sink of CO2, and so by studying rivers, you would eventually be able to calculate the rates of CO2 consumption, and then to build models and to test the hypothesis, which was proposed by Walker et al. So today we have now big database, and I would like to mention the last update on modern river geochemistry, which is a database which was constructed by Jens Hartmann from Hamburg in Europe, and it was published in 2014, and which is called Flourish. Okay, so today I would like to take one example of how we can use rivers to integrate critical zone processes. And the question which I'm interested in today is to make a complete mass budget of carbon at a very large scale, and with the application of the Mackenzie River Basin. Very few basins, if not maybe only two, river basin has been investigated by the way I'm going to show you tonight. I mean, by this investigation, I mean to make the list, all the list of all the processes which are sources and sinks of carbon within the watershed, and to calculate at the end what is the net result. Okay, so basically I'm going to, again, to test whether the Walker et al. Hypothesis works, or in other words, if the Earth surface is a way to consume CO2 from the atmosphere. Okay, and so this corresponds to a paper that we have published last year or 2 years ago. The first author is Kate Oran from Durham, and this paper is associating a number of friends and colleagues that you can see here: Bob Hilton, Mathieu Delanger, Ed Tipper, Valier Gali from Woods Hole, Damien Calmels from Orsay University, and others. And so this is a big paper which is making a synthesis of, in the catchment of the Mackenzie River Basin, of the net CO2 consumption. So tonight, to show you what are the sources and the sinks of carbon in theory, I would like to talk a little bit about the Mackenzie River Basin. I will show you how we calculated the chemical weathering fluxes, so the inorganic chemical weathering fluxes. I will then turn to the organic carbon fluxes. I will insist on the role of sulfuric acid, which is a new discovery in the field of river geochemistry, and which is totally changing the vision that Walker had in 1981. And I will talk about the oxidation of petrogenic carbon. And then I will wrap up everything, and I will give you the name of the winner. I mean, is the Mackenzie River a source of CO2 to the atmosphere, or is the Mackenzie River Basin a sink of CO2 at the end? So a little bit of theory. So this is a slide showing you the different carbon cycles. So basically, I don't want to spend too much time on that, but there are many carbon cycles actually, and so the short carbon cycle is the cycle of carbon which is associating photosynthesis and respiration. Okay, it's involving big fluxes of carbon each year, but it's a very short term, pretty much equilibrated. And so I'm not going to talk too much about photosynthesis and respiration in the Mackenzie River Basin, because I'm considering that these very short-term fluxes are equilibrated, okay? But on a longer time scale, a number of processes are consuming CO2 from the atmosphere and sequestrating it into the ocean. This is silicate weathering. This is carbonate weathering. And this is the export of organic matter that some people call weathering of organic matter, which I think is not a proper term. And all these fluxes, the red arrows here, correspond to carbon which is transferred from the atmosphere to the ocean. So if I want to make a complete mass budget of what is happening on a catchment at the surface of the planet, I must take into account all these fluxes. And this is what I am going to do today. So just a quick reminder of why silicate weathering is a sink of CO2. I have already gave you a couple of words on that. So this is a slide showing the chemical reactions associated with the weathering of silicate, a calcium silicate here on land, and the precipitation of carbonate in the ocean. So over the time scale that is characteristic of this carbon cycle, and we don't exactly know, but let's say 500,000 years, the typical time scale of that process is 500,000 years. You consume CO2 from the atmosphere, because you do see that when you weather 1 mole of calcium silicate on land, you consume 2 mole of CO2, but when you precipitate calcium in the ocean, you remove 1 mole of CO2 into the system. I mean, into the ocean plus atmosphere system. So the net result is the transfer of 1 mole of carbon from the atmosphere to the limestones here. And this is a long-term process by which probably the Earth has purified its atmosphere in CO2. If you consume carbonate weathering, you consume CO2 from the atmosphere to make this reaction here. 1 mole of calcium carbonate is reacting with 1 mole of CO2. But when calcium carbonate is precipitating into the ocean, it's exactly the reverse reaction, and then you remove the CO2 that you have consumed. So if you think about long time scale, such as 500,000 years, which is a typical time scale of silicate weathering cycle, you attempted to say that carbonate weathering is not a source of a sink, of CO2 from the atmosphere. But actually, this is not really true, because at smaller time scale, and for example, typically the time scale which humans are perturbating the system, calcium carbonate is going to matter. And when you weather, in addition, when you weather calcium carbonate, not with carbonic acid, which is a CO2 from the atmosphere, but with another source of acidity, which is provided by the oxidation of sulfide, that produce sulfuric acid, then you will have a very different situation, because you do not consume CO2 when you weather the limestone on terrestrial surfaces, but you release CO2 in the ocean when you precipitate the calcium carbonate. So, and has been published by a number of authors over the last decades, and in particular, Mark Torres published a nice paper in GC a couple of years ago, where he quantified the different timescales which are involved when sulfuric acid is used in comparison to carbonic acid to weather the continental crust. But basically, if you use another source of acidity than carbonic acid, then you will remove CO2 in the atmosphere over a certain period of time. Of course, if you go at very long time scale, the sulfate, which is added to the ocean by the weathering of limestone by sulfuric acid, is going to be reduced in sulfide, and then you will have exactly the reverse reaction that the one you had on land. And so over very long time scale, which are higher than the residence time of sulfate in the ocean, so typically 10 million years, the chemical weathering of limestone by sulfuric acid is not a source or a sink of CO2 from the atmosphere, because the equations are balanced. But on transient time scale, it's important to realize that when carbonate weathering is made by using sulfuric acid, it's a source of CO2 to the atmosphere. So these slides were about the, let's say, inorganic cycle. But there is another cycle, which is organic now, which is represented on that slide. This is a slide of the Beni River in the Andes, and you do see that on the beach of the end of the Beni River, you do see branches and residue of organic matter, which has been physically eroded from the landscape and is going to be transferred to the ocean. So eventually this carbon is going to be buried, and is going to be to represent a net sink of CO2 which has organic matter containing carbon, and this organic matter has escaped from the remineralization of organic matter in the topsoil. So organic burial is a very important process which is sequestrating CO2. But of course, you also have the reverse reaction, which is the oxidation of carbon of petrogenic carbon, of fossil carbon trapped in sedimentary rocks. And this slide is showing a typical mountain formed by organic rich sedimentary rocks. And at the surface, we don't see that on the slide, but if you go in rocks exposed to the oxygen of the atmosphere, of the modern atmosphere, are going to be oxidized just because the organic matter of the rock is very reactive in contact with oxygen and is producing CO2. So this is a reaction which is producing CO2 to the atmosphere. So it's a counter reaction of the previous one. The burial of organic matter is compensated by the oxidation of fossil organic matter from terrestrial surfaces. So you do see that it's a very complicated situation. And if you want to make a complete mass budget, you have to take all this into account. So you have to take into account the sinks, photosynthesis. I'm not going into photosynthesis processes today because, as I said, it's a very short-term process. But carbonate weathering by carbonic acid should be considered. Silicate weathering should be considered. The burial of organic carbon should be considered. These are the sinks of CO2 from the atmosphere. But you also have sources, carbonate weathering by sulfuric acid. I just showed you that this is a source of CO2 to the atmosphere. You need to take into account the oxidation of petrogenic carbon present in the rocks, and which is producing CO2 to the atmosphere. And eventually, if you have volcanoes on your watershed, you should take volcanic degassing into account. This is not the case in the Mackenzie River Basin. Okay, so I'm going to show you how we solved this problem in the Mackenzie. I'm not going into the details of all these processes and how we did exactly to get the CO2 consumption or CO2 emission numbers, but I'm going to screen the different processes here and how is it possible to use river chemistry to get the numbers of CO2 consumption and CO2 emissions for, at the end, calculating the net CO2 exchange between the atmosphere and the Earth's surface. Okay, so let me talk very, very briefly about the Mackenzie River Basin. So it's a nice, very nice catchment watershed in the northern part of Northern America. It's taken its name from the Alexander Mackenzie, which discovered or first described, the Western guy which first described the basin. It's a pristine basin, so you're not worried, you don't have to worry too much about human activities in the Mackenzie River Basin, which is not true, I agree, for gas exploitation, but you don't have a lot of pollution in the river that you should correct for. It's a relatively pristine catchment. In terms of physical denudation and chemical denudation, the Mackenzie River is not very impressive. It doesn't have very high fluxes of denudation. It's here. It's very, very different, of course, from the rivers draining the mountains of Asia, but it's not totally it's significant, and in particular, it is significant for the input of sediments to the Arctic Ocean. So this is a map showing the water discharge of the different rivers draining to the Arctic Ocean. So the Mackenzie has a significant discharge in comparison to the Russian rivers here. But if I were to look at the suspended sediment and the physical erosion, the Mackenzie is the main contributor to the Arctic Ocean in terms of sediments. So this is some pictures of the Mackenzie River Basin, the Rocky Mountains here, with rivers usually very loaded in suspended sediments derived from the glaciers. And this is pictures from the lowland with beautiful and typical meandering rivers and swampy areas. In terms of geology and relief, the Mackenzie River Basin is divided into three main parts. At the east here, you have a region which is the Slave Province, is a granitic, very old and quiescent region, not very much contributing in terms of water to the river. Here you have totally at the west, the Mackenzie and Rocky Mountains, which are essentially made of Paleozoic and Mesozoic carbonates, shells, and dolomites. And in between, you have the interior platform, which is very flat, very swampy, and which is constituted mainly of marine shells and black shells from the Cretaceous. And so the points here are the data that we have collected. So it's a very long story. I don't want to go into the details, but I have started working on the Mackenzie a long time ago, in 1999, maybe 97, maybe, and a number of students of mine have prepared PhD thesis on the Mackenzie. I just want to cite Romain Millot here, Nathalie Vigier, and who else? Damien Calmels did a bunch of work on the Mackenzie River also, and Mathieu Delanger most recently. So we have published a lot of papers on the Mackenzie River, and this is why we now are able to make a complete mass budget at the scale of the catchment. So I'm going to start rapidly by the chemical weathering fluxes. How do we determine the chemical weathering fluxes? It's pretty simple. I'm not going to go into the details here. So this is a triangle, typical geochemical diagram showing you at a first glance what is the chemical composition of the Mackenzie River. And it's very simple, basically. The Mackenzie River is rich in calcium and magnesium. It's dominated by carbonate weathering. But there is something which is very interesting, which is that the rivers from the lowlands, so in green on that triangle here, they tend towards the silicate weathering in member, which is represented by sodium and potassium on that simple diagram. This is something which is very peculiar in this catchment, and which is totally the reverse of, for example, the Amazon river basin, which is the fact that the chemical weathering of silicate is higher in the plain than it is in the mountains. And we have explanations for that, but I'm not going to go into the details tonight. And if you look at the chemical composition of the anions here, it's very clear also that the Mackenzie rivers are enriched in sulfate. So the cations, calcium, magnesium, which are the dominant cations, are neutralized not only by HCO3-, which is bicarbonate, the alkalinity, but also by sulfate. And this is something important, and I will come back on that later. We can calculate the amount of each cation, calcium, magnesium, sodium, potassium, which is coming from each of the dominant lithologies based on very classical method that I'm going to show very quickly here. For this is a typical mixing diagram that we use in geochemistry to calculate the contribution of silicate versus carbonate dissolution to rivers. So here you have magnesium sodium as a function of calcium sodium diagram, and these fields here are the typical composition of waters draining silicates and waters draining carbonates. And you do see that the chemical composition of the Mackenzie rivers are in between. So they are due to a mixing of water draining silicates and waters draining carbonate. This is not the big surprise, but again, the big surprise is that the rivers from the plains, from the lowlands, are the ones which are closer to the silicate in member, meaning that these rivers, which are in the lowlands, are more influenced by silicate weathering than the rivers in the mountains, which are dominated by carbonate weathering. I think I don't have time to go into the details of how we use strontium isotopes to constrain the origin of cations and to deduce how much of the different solutes come from the silicate end member and the carbonate end member. So I'm going to skip that. We can keep that slide for the questions if some of you are interested. I just want to mention that in the Rocky Mountains, we found something very peculiar, which is that there is probably somewhere in the Rocky Mountains, but we don't know where, carbonates which are radiogenic in strontium, which means that these carbonates have a very unusual strontium isotopic ratio. There's no way you can explain the river chemical and isotopic composition for strontium of these guys here, which are rivers draining the Rocky Mountains, if you don't have a carbonate in member which is radiogenic. And for those of you which are familiar with the geochemistry of strontium in rivers, this is a case that is also found in the Himalaya. So in a way, the carbonate of the Rocky Mountains are like the carbonates of the Himalaya. They are containing a radiogenic strontium component. We're not sure about the origin of this radiogenic strontium, but for sure it exists, and more work should be done on that issue. So we can calculate, and again, I'm not going into the details here. We used an inversion procedure to basically to solve the different mixing equations. So we have several tools we can use. We can use the chemical ratios. We can use the isotopic strontium ratios. And so we have a lot of information on the way the mixing between the different lithologies are made. And this system, which is an underestimated system, can be solved using an inversion procedure. And at the end, we are able to calculate for each of the big regions here, Rocky Mountains, lowlands, the foreland basins, the main tributaries of the Slave Province, we are able to calculate how much of calcium, magnesium, sodium, and potassium is coming from each of the lithologies that we have evidence on the mixing diagrams. Okay, so basically the model here is assuming a mixing between rain, which is not contributing too much, evaporitic rocks that exist within the Mackenzie River Basin, carbonate and silicate rocks. And so we are able to say that, for example, in the Rocky and Mackenzie Mountain, most of the soluble load is derived from carbonate weathering, but in the lowlands, this contribution of carbonate weathering is less, and the contribution from silicate weathering is higher. So why is it important, all this calculation? It is important because I want to calculate the amount of CO2, of atmospheric CO2, which is consumed by the reactions, the weathering reactions involving carbonate or silicate, because as I showed you before, if you weather silicate or if you weather carbonate, the consequence on the global carbon cycle are not the same. So you must be able to distinguish between the two lithologies. And this is what I have summarized on this diagram. So it's giving the chemical denudation rates, or I could have showed you the CO2 consumption rate. It's the same, it's proportional as a function of runoff. Runoff is basically the river discharge. And you do see that there are big differences between the different regions, and this corresponds to different lithologies. It's not a big surprise that carbonates have higher denudation rates than the granites of the Shell province. But what is interesting here is to say that is to show that the shells, which are in the lowlands, have weathering rates and then CO2 consumption rates, which are higher than the granitic rocks. This is not something which is general at the global scale. In a way, it's a peculiarity of the Mackenzie River Basin. Okay, so to summarize, we can calculate based on the inversion of chemical data. We can calculate the chemical weathering flux of each cations, sodium, potassium, calcium, magnesium, and allocate the different ions to the different contributing lithologies. This has been published by Millau et al. In 2001. And so silicate weathering is significant. So it means that there is some CO2 which is consumed, even if the temperature is low in that region, in that part of the world. Silicate weathering is significant, and that's probably due to the long residence time of water in the swampy areas of the lowlands. So let me now turn to the organic carbon fluxes. So how can I do that? So in a river, you have two types of carbon, organic carbon, which is transported. You have carbon, which is basically modern, meaning that this is carbon from the current ecosystems, which has been physically removed from the landscape and is going to reach the ocean, transported by the rivers, okay? And this is typically the case for these trunks that I'm showing here. But you have another source of carbon, which is what we call the petrogenic carbon, which is actually fossil carbon, which is contained, for example, here in these sedimentary rocks, which are outcropping on the bank of the river. And when the river is eroding the banks, then some fossil old carbon is going to be transported. And so if I want to make a proper carbon burial budget, I need to distinguish between the two. And this is what we've been in Mackenzie. We're using, I'm not going into the details, but we are using depth profiles where we sample with depth the different suspended sediments. And by doing that, we get access to a range of size. We have a gradient of grain size that allow us to work on several types of sediments. The bottom sediments are usually coarser than the sediments which are transported at the top of the river. Here is my colleague Valier-Gali, that some of you probably know, which is a real Superman. If you need someone to carry very heavy material on a boat and do impossible things, he is your man. And so we did, with Bob Hilton, we did carbon-14 to identify, to distinguish between these two sources of carbon. Why? Because the modern carbon contains modern carbon, which is carbon with a significant amount of carbon-14, but the petrogenic carbon does not contain any carbon-14 because this carbon is dead, because this is old organic matter. And so not going into the details here, but basically using the depth profile, we are able to see that for the different tributaries of the Mackenzie River, here is the Peel, the Red Arctic, here is the Mackenzie and the Liard River, we can calculate how much of the organic carbon is petrogenic, so old carbon, and how much of the carbon in the sediments. I'm talking about the sedimentary load here, the particulate load, how much of this carbon transported into the solid phase is modern. Okay, and so we see here in the Mackenzie, and it was very interesting to see that, is that you have a mixing for each of the tributaries, visible on the depth profiles. You have a mixing between old carbon, so fossil carbon, which is preferentially transported at the bottom of the river, and modern carbon, which is not really modern, because if it would be modern, it would have been a fraction of 1. But you do see that it's not 1, it's 0.4, 0.5, meaning that this carbon has an age, actually. And if you calculate the age that this carbon transported at the surface of the river in the sediments should have, it is something like 4 or 5,000 years. So this is one of the findings of the paper that we published with with Hilton in Nature a couple of years ago that the Mackenzie River is transporting biospheric carbon to the ocean. But this biospheric carbon is not new. It's carbon which is derived from the peatlands, peatland areas of the catchment probably, or the soils of the catchment, and which is basically old. Okay, we are releasing carbon dating back from 5,000 years. And now this carbon is being transported to the ocean. And of course, we are also transporting old carbon, petrogenic carbon, that we need to correct to come up with a flux of carbon burial, organic carbon sequestration. And so this is a calculation that we did. And so we are able to calculate a flux. I'm not going into the details here of the numbers. A flux in teragram of carbon per year of biospheric carbon, which is transported to the ocean, and petrogenic carbon, which is transported to the ocean. But just let me notice that 2.2 teragram of carbon per year are represented by particulate organic carbon of biospheric origin, and the silicate weathering is consuming 0.7 teragram of carbon per year, the numbers that I've showed you before. And so you do see here very clearly that the sequestration of organic carbon is much more efficient than the sequestration of inorganic carbon by silicate weathering. And this carbon is not really modern, it's old, but I'm not going to detail that tonight. So probably landslides, which are occurring everywhere in the Mackenzie Basin and which are more important now because of global warming, are probably releasing carbon which was sequestered in the soils, in the peatlands, and putting this old carbon, or modern but not really modern carbon, into the river. Okay, so an important process in the Mackenzie is due to sulfuric acid. And as I showed you before, the Mackenzie River waters are rich in sulfate. And with Damien Calmels, in 2007, it's not a couple of years anymore ago, we published a geology paper in which we showed that the origin of the sulfur was sulfide oxidation. I'm not going to go into the details here. You can read the paper if you're interested, but basically the idea is that we can use sulfur isotope and the oxygen isotope of the sulfate molecule to constrain the origin of the sulfur, of the sulfate, which is dissolved in the river. And you need the two isotopic ratio. If you just get one information, sulfur isotope or the oxygen isotopes, you cannot be conclusive. So you need the two. And this diagram here, which is a plot of sulfur isotope as a function of oxygen isotopes from the sulfate molecule, shows clearly that most of the sulfate is derived from the oxidation of pyrite. In two conditions, an oxic or anoxic conditions. I'm not going into the details, but that for a couple of tributaries, in particular tributaries in the Rockies, you need some sulfate coming from gypsum. And of course, if I want to determine the amount of sulfuric acid which has been used by chemical weathering, I need to get rid of this sulfate coming from gypsum because I don't want to include it into the weathering budget. Okay, this is sedimentary sulfate, and it's not derived from the oxidation of pyrite in the critical zone, and it's not contributing to carbonate weathering. And this is what we did in this paper. And we were able to show that in the Mackenzie River, if you have, this is relative units, okay? So this is basically the atmosphere, the river water, the ocean. So we calculated that if you get 100 moles of HCO3 minus reaching the ocean from the Mackenzie River, then 38 have been consumed from the atmosphere. But because the main mechanism is not weathering of carbonate by carbonic acid, by the weathering of carbonate by sulfuric acid, it's producing CO2 according to the reaction that I've showed you before, and that's producing CO2 to the atmosphere, and the number is 50. So you do see that you have consumed by carbonate weathering using carbonic acid 38% of the CO2, but you are removing 50%. So on a net budget, the weathering of carbonate is a source of CO2 in the catchment. This is what we published in 2007 in the geology paper, which was one of the first mass budget done on carbonate weathering by distinguishing between sulfuric acid and carbonic acid. And then the last term of the mass budget is the oxidation of petrogenic carbon. How much of carbon is being oxidized by the oxygen of the air, and is producing CO2. This is really a difficult flux to calculate, to constrain. And here I'm going to show you a work that have been done by Mathieu Delinger in Durham and Paris, which is to use rhenium. Rhenium is a very rare element. It's difficult to measure. It's very low concentrated. It's a platinoid, but it has a very interesting property, which is that it is coming with organic matter in a rock. So here you have a compilation which was published by the Woodall group a couple of years ago, which showed that in sedimentary rocks, the more carbon, organic carbon you have, the more rhenium you have. The concentration increases with the carbon content. And when you look at the soil profile, this is a soil profile developed on a organic rich bedrock here, you do see that the rhenium is decreasing very much when you enter into the weathered zone here, where the organic matter has been oxidized. And this is not a big surprise, because rhenium is a very soluble element, and which is transported in rivers as an anion. It's very low concentrated, but it's very soluble. So maybe we have the good tracer that will allow us to quantify the oxidation of organic matter in the landscape. Because if we are able to measure rhenium in the Mackenzie, or in general in rivers, dissolved in rivers, then we can get an idea of how much organic matter has been oxidized at the scale of the watershed, and we can come up with a flux. This is basically the idea. It's a little bit more complicated, because in geochemistry it's always a little bit more complicated, but we have methods allowing us to distinguish the rhenium which is derived from the oxidation of organic matter, which is what we're looking for, from the rhenium which is derived from the silicates, and the rhenium which is derived from the sulfides, because these two minerals also contain a little bit of rhenium. I'm not going into the details, but this allowed Mathieu to calculate the flux of CO2 produced by the respiration, which we call the respiration of mountains. In other words, the transformation of organic matter from the sedimentary rocks into CO2. And so this is, you can see in the paper, you will find in the paper the details. But the flux that we calculated for the Mackenzie River at mouth showed that there is a significant amount of CO2 which is produced this way. It's still lower than the carbon burial, but it's not negligible. So I now come to my almost final slide, which is the winner? Is the Mackenzie River source of a sink of CO2? And this is summarized on this slide. When I have where I have put all the input and outputs to the atmosphere and ocean system by the different mechanisms that I have explained to you earlier. Okay, so just an example. This is the amount of CO2 0.89 here, which is consumed by carbonate weathering, but this is the CO2 which is consumed by carbonate weathering, but this is compensated by an equal amount of CO2 which is returning to the atmosphere just because this is carbonate weathering. This is a silicate sink, this is the carbon burial sink, etc. So let me do the net calculation, and when you do the net budget, the calculation, the final calculation, you do find that there is a net consumption of CO2 from the atmosphere, which is from carbon from the atmosphere, which is transformed and transferred to the ocean. So we are happy. The Walker et al. Hypothesis is still valid. The Mackenzie River catchment is still a sink of CO2 from the atmosphere, okay, on a long-term perspective. And so this is the detail of the calculation. And you see that this equation that allows you to calculate the -1, which is the 1 ton of carbon per square kilometer per year, this calculation strongly depends on this term here, which is the highest term of the equation. And this term is what? This term is the organic burial, okay? So this calculation shows that the modern biospheric sequestration is the most important term of the budget. And if you change it, then you're gonna change this, the net consumption or emission of CO2 from the catchment. Okay, so if you have more vegetation, for example, if you warm up the climate, vegetation will grow up and probably organic carbon burial will increase. And then you will increase this flux here. And so maybe you will change the global the global mass budget of the Mackenzie in terms of CO2 consumption or emission. Okay, so the conclusion of the study is that chemical weathering and organic weathering both result in a net sink of atmospheric CO2. We have, as I showed you, tools to investigate for over large river basin this kind of approach. And this is what is needed now, because we don't have a global idea. Okay, we don't know what at the global scale. When we will combine all these processes, CO2 consumption by silicate weathering, the use of sulfuric acid to weather carbonates, organic burial, petrogenic carbon oxidation, we don't know at the global scale what will be the result. And a number of teams are still working on that issue. Some people, for example, Mark is working on that problem in the upper Madre de Dios upper tributaries on the Amazon And so the conclusion I'd like to give here is that we have the tools. Okay, the rhenium is probably not a perfect tool to deduce the amount of carbon which is being oxidized, petrogenic carbon which is being oxidized, but it's not bad and it's working, I think, quite well. And so we need to do that at a larger scale. there is one paper which was published last year. Actually, was published exactly at the same time as we published our paper on the Mackenzie. This is a paper by I don't have the reference here. It's a paper by the group at ETH. We calculated the same kind of carbon budget that I've showed you here on a smaller watershed in Taiwan, and the result is exactly the one that I have showed you here. A big importance of organic carbon burial, but on the whole, the catchment is still a sink of CO2, a sink of atmospheric CO2. So I think I'm gonna stop here. Just by this slide, in 2011, Yves Godery's team published this paper in Nature Climate Change. It's, according to me, according to my knowledge, is the first paper that a river geochemist have ever published in Nature Climate Change. Okay, meaning that climatologists are starting to realize that rivers are important, and in particular the type of study that I've showed you tonight is important. We need to know, to have a better knowledge of the different processes which are consuming or emitting CO2 on terrestrial surfaces, and because we need to be able to predict what is going to happen when the CO2 in the atmosphere will double, and when the temperature will increase. And catchments or watersheds like the Mackenzie River Basin, as you know, are going to warm up a lot in the future century. So this is really crucial to better know what is happening today in order to be able to predict what is going to happen. And with this, I can take questions, and I thank you for your attention. Thank you.
All right. So, but I do think we should end it there. And we thank you very much for coming. And I'm going to end the meeting here, and please join us for the DeFord next week.